So, in this lecture, we are going to talk about fully nonlinear equations, right? So, most of the problems which we encounter in daily life, I mean, if you want to, model certain phenomena, they actually tend to be nonlinear equations. So, we are obviously going to start with the first order, first order nonlinear equation, fully nonlinear, okay, fully nonlinear equation, okay, with into variables. Now, what happens in n variables? Exactly same thing, yeah. Nothing changes. If you want to do it, you can do that. But for now, we are just concentrating on two variable because it is much easier to comprehend what is going on. Okay, so let us talk about a general problem. What does it look like? So, general problem looks like this: f of x, y, u, ux, uy is equals to 0. Okay, and so sometimes it is written by f of x, I mean, or sometimes, so this can be also written like this, yeah, f of, let's say, x u and gradient u equals to 0. Okay, in this case x will be considered in R2, u of x is in R, so u of x will be in R, and gradient of u at the point x will be in R2, right? Okay, and here it is just broken up into x is in R, y is in R, u of xy, ux of xy, and uy of xy, right? It is written in this way, and of course u restricted to some gamma is phi. Okay, and what is gamma? Gamma is a smooth curve in R2, right? So this is given to you, this is the problem which is given to us, and we want to solve this problem. So that's your one. Now, fully nonlinear equation, I mean, you can think of this like I mean, for an example, let's say an example of this kind of equation may look like this: ux times uy equals to 1. Yeah, as you may I mean, just looking at the expression, you can see that if you want to write characteristic equations or not, it is not the right form, right? Because initially what we were doing was the form was something like this: ux plus buy equals to c. I mean, abc can depends I mean, the dependence of abc can be on x, y, and u, right? At most for quasi-linear, and same for goes for b and c. Yeah, so that can happen. But the thing is, this kind of equations, they are not in this form, right? So there is no way we can use the exact same thing to work out this kind of problems, right? But I mean, we will use the same kind of thing, but we need an extra condition. That's what we are saying. So essentially, equations like this, or let's say another equation like ux square plus uy square equals to 1, let's say. Yeah, this is also does not fall in this category because a and b, c, these are functions of x, y, and u, not x, y, u, ux, and uy. Yeah, so those are fully nonlinear equations, right? Now we want to talk about this sort of equation, and we want to see if we can how to solve this equation, right? Now we want to do same sort of thing. We want to write some characteristic equations, and we want to write the solution of this thing. Okay, so first of all, we want to find the characteristic equation. Question is how to find such a characteristic equation. Yeah, see, we will take our ideas from whatever we already know, because you see, our characteristic equations should be such that this is a fully nonlinear equation, so this equation definitely contains all the semilinear. So basically, any linear problem, any semilinear problem, any quasi-linear problem can be written in this form, right? Okay, so our characteristic equation should be such that these linear, semilinear, and quasi-linear equations can also be taken care of. So exactly the same sort of equations should work, right? Okay, so what I mean by this is, let's say that I have an equation. So let me motivate you how we are going to do that. See, I let's say I have an equation something like this, yeah? A quasi-linear equation: b of x, y, u, uy equals to c of x, y, u. right? And of course, let's say u restricted to gamma is phi. Now we know that we can use our usual thing, right, for this quasi-linear equation to write down the characteristic equations. Okay, so by letting z of s, okay, to be u of xs and ys, we can define the characteristic equations as x prime of s. Okay, I mean, for now, I'm not trying. You understand this? This is for a fixed r. Okay, this is for a fixed r. X prime of s equals to a of x y u. Y prime of s is b of x y u, and z prime of s is c of x y u. Yeah, this is there. So this is for this equation. Now you see, you can of course, realize that this A, B, C, this equation can be written in this form. Of course, we can do that for some f and phi. Now the thing is, we are going to take our q from here and write down the characteristic equations for our original fully nonlinear problem, for this problem. You understand what I'm saying? See, since this is a special form, the quasi-linear equation. This is a quasi-linear equation, right? This quasi-linear equation is a special form of 1, right? And we know how to write the characteristic equations for the quasi-linear equation. So motivated by this idea, we are going to write the characteristic equation for this equation, right? Okay, how to do that? So for that, what we are going to do is we are going to start with defining some variables, okay? So introducing some variables. So what we are going to do is introduce some variables, okay? And how are you going to do that? We are going to introduce a variable p of s, which is u of x with respect at the point ys, x's and ys. So essentially what we are doing is, see, initially here it was, u we are writing as z, right? U at the point x's and ys we are writing as z of s. Here u of x at the point x's and ys we are writing as p of s. Clear? Okay. And so this is p of s, and similarly q of s we are going to write it as uy at the point x's, ys. Okay, see, this is not for every xy. On the characteristic curve xs ys, yeah, the characteristic curve is given by xs ys, and ux on those curves, that is given by p of s, and qs is u of y. So those are the two variables which we are going to define. Okay, and if you rewrite, so rewrite, let's say q as f of x y z p q. Okay, this we are writing it as a x y z p plus b of x y z q minus c of x y z. This is 0. Yeah, so I'm rewriting q as this, right? Okay, once I do that, see the characteristic equation, then the characteristic equations, yeah, are to satisfy this, satisfy x prime of s for a fixed r, of course. Okay, x prime of s. So see, now I am not really concerned about whatever what the initial condition is. Yeah, you can obviously put the initial condition here, but for now let's just write down the characteristic equations. So this is f of p x y z p q. I hope this is fine. X prime of s is f of p, right? Of course, because f of p, if you see, this is a function you are just defining. Let's say this is a of p plus b of q plus minus c, right? F of p is this particular thing with respect to p. See, think of this as the independent variables, okay? So this becomes only a, because you can't take the derivative of this with respect to p. That will be 0. Yeah. So it's just a times dp, the derivative of p with respect to p, which is 1. So this is x prime of s is a. Yeah, and what is A? A is fp, right? Yeah? So that is why we are just writing this thing in terms of f of p. And similarly, if you want to write y prime of s, what is it? It is fq at the point x, y, z, p, q, right? Now let's see if I want to write what is z prime of s. See, z prime of s is c, right? I mean, z prime of s should be c. So how to get that c? So for that, you just look at this thing. You just write it as p f of p plus q f of q. Okay, and that will give us, z prime of s. Why? Because you see, f of p is a, f of q is b, right? So pf of p is, so therefore it is pa plus qb, right? Pa plus qb, you see, pa plus qb is c, right? Which is c. So that is why we just write z prime s like this. Okay, so this is the motivation. See, the whole idea is this. Initially, there was like a specific form, which is a ux plus b uy equals to c. Here, we do not have a specific form. We have a generalized form. We want to write it in that form. Okay, so our characteristic equations should contain not ABC but should be in terms of F. So using that idea, initial idea, we are just writing it in terms of FP, FQ, Z prime of this is PFP plus QFQ. Okay. Now the issue here is with these three equations. Okay. So the issue is this issue. These three equations, okay, are not sufficient to solve fully nonlinear problems, nonlinear equation. Okay, so you can take easy equations and you can see that there is no way with the help of these three equations. Okay, with the help of these three equations, you can actually solve a problem. See, up till quasi-linear, the thing is this: up till quasi-linear equations, these three equations with the obviously the initial conditions, okay, are sufficient to solve the problem. But for non-linear equations, okay, things get a little complicated. Okay, and now to handle those things, what we do, we have to create new equations. Okay, so you need more information on the problem. To get that more information, what we are going to do is we are going to take the derivative of this P and Q. Okay, so what is P? P is ux and Q is uy, right? On xs, ys, on the curve. So along the curve, xs, ys, okay, we have dp by ds. Okay, this is d ds of ux, right? Okay, and that is given by, see, ux depends on x and y, right? And which again depends on s. So we have to use chain rule here. So this is uxx and x with respect to x, so x prime of s, plus ux with respect to y, so which is uxy, and y prime with respect to s. Okay, so that is what you are going to get with this. Now you see, I don't want to write ux. I don't want to involve any second derivative like this. So I will just write it like px x prime of s plus py y prime of s. Okay, let me write it like this. Now you see, what is x prime of s? It is given by fp. So we can write it as p of x f of p plus p of y f of q. Okay, and similarly you can also do it for dq ds, right? Dq ds, and that, exactly the same thing will happen. And let me just write it down. It is qx f of p plus q of y f of q. Okay, right. Now what happens is this: we want to write this thing in a much easy manner. You see, I do not want our px and py, all of these things I don't want. You understand? See, the whole point of this is the characteristic equation should be written in terms of f. So here it is fp, here it is fq. Okay, PFP QFQ is fine, but I don't want PX PY, all of these things, because the thing is, the more variables involved, the more complicated it gets, right? So I have to somehow get rid of this PX and PY. How to get rid of that? So see, I have this equation which is given by f of this 1. Okay, so that equation, if I differentiate, okay, so let's say differentiate f with respect to x, we get see, the question is this, we want to replace this country f px py qx qy. F of p, f of q, these are fine. I know what f is, right? So I can take the derivative with respect to p, derivative with respect to q, and then put it here. I just want to find what px py qx qy are, and for that I am again going to use f. So if I take f and derive it with respect to x, what do I get? I get df by dx, let's say. That is f of x. F depends on x, first of all. Yeah, fx, f with respect to x, and x with respect to x is 1, plus f of y and dy by dx, right? That is there. So that is, with respect to y, if you are differentiating x, that is 0, plus f z. Yeah, so with respect to u, f of x, see, f depends on x, y, u, ux and uy, right? Okay, so initially the derivative of f with respect to x, okay, and dx by dx, okay, that is 1. That is why f of x. Derivative of f with respect to y, and then dy by dx. So here dy by dx, what it means is you are differentiating y with respect to x. Since y, these are, we are thinking of it as the independent thing, so that is 0, right? And then this is your z variable, so differentiating this with respect to z, you get fz, and times u with respect to x, right? So it is ux plus f of ux, right? So f with respect to ux is p, so it is f of p, and ux with respect to x, which is uxx, and this is f of q uxy, right? Okay, so this is just a chain rule. So this is chain rule again. Chain rule. Okay, so this is 0, right? First of all, why it is 0? Because f is given to be 0. So the derivative of 0 function is also 0. So this is 0. So if this is 0, what will happen is we are going to get px. Okay, this is what? This is px, f of p plus py f of q equals to minus f of x, okay, minus p f of z. This is p, right? F u of x is p. So this is another thing which you are going to get. Okay, maybe I can just write it like 3. These 3 equations are 3, and then I have another equation which is this. This is 4. Okay, and similarly you can take the derivative of f with respect to y, and you can actually show the df dy, which will be something like this with respect to y. Okay, and if this is 0, you will similarly you will also get this equation qx f of p plus qy f of q equals to minus f of y minus q f of z. Okay, that is 5. Okay, so similarly, this is with respect to x I'm doing, and with respect to y, if you do, you can just find it. If you're not convinced, please check this. This is just a one-line thing, nothing else is there. Okay, so what are the characteristic equations there? Therefore, the characteristic equations are given by x prime of s. X prime of s is f of p. Okay, f of p obviously depends on x, y, z, ux, p, and uy, q. Okay, again similarly y prime of s is f of q, which is again depends on this pq. Okay, and z prime of s is pfp plus qfq. pfp, okay, plus qfq. Okay, I obviously it depends on x, y. I am not writing all that. Please write it down if you want to. And you have more. You have p prime of s is minus f of x, okay, minus q p f of z. This one here, minus f of x minus p f of z, and q prime of s is minus f of y minus q f of z. Okay, so these are the characteristic equations which we get. Now the question is this is fine, yeah. How do I find the initial condition? So now question is to find initial condition. So essentially u restricted to gamma is phi given, okay, and gamma is characterized by gamma 1 of r, let's say, and gamma 2 of r. Okay, that is parameterized. Gamma is parameterized by gamma 1 of r to gamma 2 of r. So of course there are, you can obviously write, so let's say this is for a fixed r, okay, so xr is for a fixed r. If I want to write the equation with respect to r, x at the point r0, so s equals to 0, okay, s equals to 0, what happens here? See, the projected characteristic phi, okay, sorry, the data curve gamma times gamma and phi, that is gamma 1, gamma, sorry, let me write it this way, I wrote it. Gamma is parameterized by gamma 1 and gamma 2, right? So x at the point r0, this is given by gamma 1 of r, right? X at the point r0 is given by gamma 1 of r and gamma 1 of r, yeah, because that's the first thing. And y at the point r0 will be given by gamma 2 of r, okay. And similarly z at the point r0, so this is s equals to 0, okay. How will I write it? It is z at the point on the curve gamma, right, at the point r0, so that is phi, okay. So this is given by phi of r, clear. And now I do not have information on these two. This is what we need to find. So it is, see, this is just the usual thing which we know, I mean there is nothing special about this thing. We just want to find two other initial conditions, okay, and how to find those initial conditions. So first of all, you see, so these two question, these two we don't know, okay. Now how to find this thing? See, whatever initial conditions are, they must satisfy the PDE first, okay. So the initial conditions, the new initial conditions, so P and Q, the initial condition on this, the initial condition must satisfy the PD, right? That is obviously the case. So essentially, I am looking for this thing. I am looking for what is P at the point R0 and what is Q at the point R0, right? So this is the two things which we want to find. So if this satisfies the PD, what do we have? We have that let's say psi 1 of R is P of R0, okay, and psi 2 of R is Q of R0, okay. So we are assuming this is psi 1 of R and psi 2 R. We don't know what is psi 1 or this is the unknown, psi 1 and psi 1 and psi 2, these are unknown. We are just writing it. Let's say that, I mean, P at the point R0 is psi 1 and Q at the point R0 is psi 2. If this happens, then this must satisfy the PD. So essentially what we have is f of x. So f of gamma 1 of R, gamma 2 of R, okay, and phi of R, psi 1 of R, psi 2 of R has to be 0. Yeah, this is true. Because why this is true? Because the initial conditions has to satisfy the original problem. See, I don't know what is P at the point R0 is and Q at the, so let us assume that is phi 1 and phi 2, okay, and then that will has to satisfy this equation, okay, right. So this is one condition. Another condition, okay. So the question is this: how do I find psi 1 and psi 2? Psi 1 and psi 2 can be found out with this equation. That's the thing. This is not, see, this is just a one relation, right? And we have two, psi 1 and psi 2. So we need another relation also. So let me write it like 5, 6. That's the sixth thing. And for the second equation, how do I find the second equation? For the second equation, what we are going to do is we are going to take the derivative of u with respect to r, okay, at the point r. So that will give you del u del x, okay, x prime of r plus del u del y prime of r, right? So that is what we are going to get. See, u, okay, we are just taking the derivative of u with respect to r. That's what we are going to do, okay? And we are hoping that we get some relation out of that. So from there we get this thing. So what is this? This is psi 1 and psi 2, okay? What at the point r0, what should it satisfy? You see, u with respect to r. Okay, so del u del r basically. So that is phi prime of r, right? See, u at the point r0, okay, so on the curve u is phi of r, right? So u with respect to r is phi prime of r, yeah? And what is del u del x, yeah? Del u del x is p at the point r0. So I'm just assuming that this at s equals to 0. At the point r0, this is psi 1 of r, right? And this is x prime of s. What is x prime of s? This is gamma 1 prime of r. Why? Because x at the point r, see, this is for s equals to 0, okay? This is evaluated at s equals to 0, at s equals to 0, okay? So x prime at the point r0, x at the point, see, x at the point r0 is gamma 1 of r, right? That's the initial condition. So x prime at the point r0 is gamma 1 prime of r. So this is gamma 1 prime of r plus, what about this? This is psi 2 of r, and this is gamma 2 prime of r. Clear? Okay, so this is how we are going to get. So this is 6 and that's your 7. So it's a bit complicated, but I mean we can get through it. Okay, so this data is called admissible data. So I will just define a small thing. It's called admissible data. Okay, so what is an admissible data? The initial data, okay, gamma, which is given by gamma phi and psi, okay, so which is given by gamma 1, gamma 2, phi, psi 1 and psi 2, okay, which satisfies 6 and 7 is called admissible data. Clear? It's called an admissible data. Okay, and you can actually, the existence theorem which we proved earlier, you can use that existence theorem and you can actually find a unique solution. Okay, so here let me write down the non-characteristic. Okay, when do we say something is a non-characteristic curve? Okay, so the boundary data, okay, gamma, phi, psi 1 and psi 2, okay, is called a non-characteristic, non-characteristic okay, if you have this following: fp at the point gamma 1 r, gamma 2 r, phi r, psi 1 of r, psi 2 of r, okay, and fq of gamma 1 of r, gamma 2 of r, okay, phi of r, psi 1 of r, psi 2 of r, okay. So you remember the non-characteristic condition, right? A dot b. A is f of p, b is f of q. So I'm just writing it in terms of f, right? The exact same non-characteristic condition, but here it is just in terms of f and f of p and f of q, minus gamma 2 prime of r, gamma 1 prime of r. This has to be non-zero. So it is very clear, right? The exact same non-characteristic condition here, just a and b are going to get replaced with f of p and f of q. Okay, and of course, I mean, you have the existence theorem. You can just prove exactly in the same way. You can actually say that if you have a admissible data, so essentially, I mean, give you the existence theorem later. So existence theorem is basically this: if you have a initial data, which is a admissible initial data, okay, and if the data curve is a non-characteristic curve, so if a admissible data is a non-characteristic curve, okay, and it solves the characteristic equations given by this, 1 to 5. If it solves all these non-characteristic equations, then you have a unique solution locally. Okay, so that's the thing. But I mean, we can write it in a much better way. But first, let me give you an example of how to solve this thing, yeah, and then we will write down the exact form. Y square equals to 1, and u restricted to gamma is 0. Okay, where gamma is given by x square plus y square equals to 1. Okay, this is in xy plane. Clear? Okay, so here what is am I doing? Ux square plus uy square equals to 1. This is the problem we need to solve, and it is restricted to this unit circle. Okay, so let us rewrite this problem in terms of x, y, z, p and q. It is p square plus q square minus 1, that is equals to 0, right? That is given. So the characteristic equations, let us write it down, are given by, you remember x prime at the point r is, what is it? It is fp. It is a, right? And a is fp. So basically here, if we are taking this with respect to p, it is 2p, right? It is 2p. Y prime at the point r is fq. Okay, what is fq? F with respect to q. So f is this with respect to q. This is 0. So think of this as independent variable. This is 0. So f with respect to q is 2q. Okay, z prime rs. What is z prime rs? Z prime rs is pfp plus qfq, right? So 2 times pfp, p square plus q square. Okay, okay. Now what is p prime rs? P prime rs is minus fx minus p fz, right? That's p prime. Now if you calculate this thing, minus f of x 0 minus p f of z 0, so this is 0, and q prime rs is similarly minus f of y minus q f of z. Okay, and that is again 0, because this function f is independent of y and z. Now if you parameterize, I mean, you see, this is a unit, gamma is a unit circle, right? So gamma can be parameterized like cosine r sine r. Of course we can do that, right? Okay, so you parameterize it like this. Okay, now what are the conditions which you find? X at the point r0, what do you think that is? X at the point r0 is cosine of r, right? Cosine of r. Okay, what is y at the point r0? Y at the point r0 is sine r. Okay, what is z at the point r0? Z at the point r0 is, so first is cosine r, next is sine r. Z at the point r0 is, so you are basically looking at what u does at the point, I mean, cosine r sine r, it is always 1. Okay, because cosine square plus sine square is 1. So z at the point r0 is 1. Sorry, z restricted to gamma is 0. So z on this circle is 0, right? So this is 0. Huh? Sorry, it's not 1. See, z is u, right? Z of s is defined as u of xs ys, right? Okay, for a fixed r, Okay, so at the point r0, this is z at the point 0 is u at the point x at the point 0, y at the point 0. So essentially that is u at cosine r sine r, and that is 0. Okay, so z at the point r0. Now I need to find, let's say p at the point r0 is psi 1 of s, and q at the point r0 is psi 2 of s, right? Now I need to find what psi 1 and psi 2 is, and then we can just solve the equation and get our answers. Okay, how to find psi 1 and psi 2? So for that we want to use 5 and 6. Okay, so first of all, psi 1 and psi 2 satisfy the PD. Okay, so first thing, psi 1 and psi 2 satisfies the PD, right? So what happens if it satisfies the PD? I have psi 1, psi 2 prime are, sorry, this is square, 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 this is 1, right? How is it coming? See, psi 1 and psi 2 must satisfy the PD, right? F, here it is f of this, psi 1 and psi 2 must satisfy f of this, right? And here f is given by p square plus q square equals to 1. Okay, so essentially, if this is true, see, this is true for all RAs, right? So this is true, right? P square at the point R0 plus q square at the point R0. Okay, so this has to be minus 1 is 0. This has to be true. P at the point R0 is psi 1. Okay, so see, this is psi 1 of R. It should be not S, it is R, sorry. S is 0. It is just a function of R. Okay, so this is psi 1 of R square plus psi 2 square of R, right? Equals to 1. Okay, so that is why I am getting this relation. From this relation, you get some conditions, but we need another condition. Okay, and for that, I have another condition, the seventh condition. You remember, seventh condition. So psi 1 gamma 1 of R plus psi 2 gamma 2 of R. Our gamma 1 is cosine and gamma 2 is sine, right? Yeah, so that is given, and that is equals to phi prime of R. Okay, so let me write it down here, what it gives. And phi prime of R, phi prime in our case is 0. So this is 0 equals to phi 1 of R, okay, minus sine of R plus phi 2 of R cosine of R, right? That is what we are going to get. So now you have to solve these two equations. It's not very difficult to solve these equations, right? Now if we solve these two equations, so let's say this is, let's write it like A and B, okay? So solving A and B, solving A and B, one gets two relations. So number one, either psi 1 of R, okay, equals to cosine of R, and psi 2 of R is sine of R. Okay, see, either this relation satisfies this, and even this also, because cosine R minus sine R, cosine R plus cosine R sine R, that will be 0. Either this or just the same thing with the sine, okay, minus sine, minus cosine of R, and psi 2 of R is minus sine of R. So either this or this, huh? Whatever you can choose. Now let's choose the first condition. So one gets either A or B, right? Okay, now let's choose one. So let us choose, okay, 1. Okay, so in that case, if you choose 1, then these are our characteristic equations, huh? Characteristic equations. This turns out to be cosine of R, and that is sine of R, right? Okay, so if you do that, these two conditions, so if you are choosing 1, then P of R0 is phi 1 of R, which is cosine of R, and Q of R0 is phi 2 of R, which is sine of R, right? So you get those two conditions, and then with those two conditions you can solve. Then one can solve the characteristic equation C, okay, and what do you get in that case? Then see, to get this, you see, P prime is 0, yeah, with respect, and this prime is with respect to S. So P is constant with respect to S, and P at the point R0 is cosine R. So P is cosine. P of R for every S is cosine of R, and Q of RS is sine of R, because this is constant with respect to S. Hence, P of RS is cosine of R, and Q of RS is sine of R. Is it clear? Why? Because P prime is with prime. What I mean by this is with respect to S. P prime is 0. So P is independent of S. Okay. P at the point R 0. At S equals to 0, P is cosine R. So for every S, P is cosine R. And similarly for Q. Okay. Now I can also find what X and X, Y and Z is. Okay. So for this, I am just going to write what X of R is. Okay. If I calculate this thing, I will get it is 2R plus 1 cosine of R. Yeah, please check this part. It is actually very easy to solve. It is 2s plus 1 sine of R. Once again, this is S. I wrote it like, okay, it is 2s plus 1, 2s plus 1 sine R, and Z of Rs is 2s. Okay, so please check this part. I mean, this is not very difficult to see, but please check. Okay, once you check this thing, you can see that the solution is given by, okay, you just replace S from here, okay, and once you do that, see, x square plus y square is basically 2s plus 1 square, right? 2s plus 1 square, which is z plus 1 square, right? So the see, x square plus y square is equal to 2s plus 1 square, right? And 2s is given by z, so this is basically z plus 1 square, right? Okay, so that's your solution. So it's given by z is u, so u plus 1 square, this is x square plus y square. Okay, x square plus y square, and this will imply u of x is equals to minus 1 plus root over x square plus y square. Okay, so this is our solution. Now, why am I writing plus and not minus? So there, if you take the square root, this is plus minus, right? There will be a minus sign. But if you take this minus sign, so this is true because ux equals to minus 1 minus root over x square plus y square, okay, is not a valid solution. Why is this not a valid solution? Because you see, u restricted to the point x square plus y square equals to 1 is 0, right? If you put x square plus y square equals to 1 in this thing, it is becoming minus 2. Okay, so it is not a valid solution because it does not satisfy the other solution. From here, you get u equals to minus 1 plus minus root over x square plus y square. The minus part, this part, is not valid because it does not satisfy the initial condition. Okay, let me write it down. Because it does not satisfy the initial condition. Okay, so this is with the one, I mean, if you remember, we just chose the first psi 1 and psi 2. If you choose this psi 1 and psi 2 minus cosinus psi 2 r, so again choosing psi 1 r to be minus cosine r and psi 2 r to be minus sine r, you can do the exact same thing and you can say that u of, sorry, this is u of xy, yeah? Making some mistakes here. This is u of xy, x comma y. It should be x comma y because u is a function of two variables, equals to minus 1. Okay, let me write it properly. It is becoming very confusing. It is u of x comma y, which is this. Again, here also we have to write it u of x comma y equals to minus 1. Okay, so I think this is fine. Now similarly here, choosing this initial condition, if you choose, then you get the solution u of x comma y to be 1 minus root over x square plus y square. That's your value. Here also you will get 2, but one of them will look like 1 plus this thing, and that will not satisfy the initial condition. So this is the solution, valid solution. Okay, so you get two different solutions out of this. Clear? So with this, we are going to end this lecture.